Hi everyone, welcome to this session, Auto Fragment Modeling Introduction. So I'll start with the background introduction. Why are we interested in heavy hydrocarbons? So one of the reasons is that it's the starting material for lighter hydrocarbons, and we can know the potential of some light product generation. And it could be useful for improving the current refining processes or searching for some applications such as polymer recycling. So instead of doing experiment, why are we trying to do it by simulation? And what is the advantage of making a kinetics model? So the first reason is that we sometimes we might not be able to conduct experiments under some conditions. And we can get a sense about the chemistry of a system of interest, which we probably do not have data by hand. And we can also use it to help us predict some observables, such as product yields. And what techniques can we use to build kinetics model? So there are two main categories. The first one is the simplified method, which is called the lumping method. It usually combines similar species together into groups. And we usually do the lumping based on what we can observe experimentally. For example, aliphatic species versus aromatic species. And the second one is the detailed model, which basically tries to track every molecule, including every isomers during the model generation. And here is a brief comparison table for both methods. So the reason to add all the extra complexity in the detailed model is that we can save the effort to conduct experiments to get fitted rate coefficients, and we can avoid inaccurate extrapolations from the fitting conditions. And also, hopefully, it can capture some cross reactions with rate estimated from first principles. So one of the software which can help us to build kinetics model automatically is on reaction mechanism generator. So I believe everyone who is watching this video is probably familiar with RMG. So what can RMG achieve? We can have high extrapolation flexibility model because it's basically showing the fundamental chemistry and it's the most detailed level of mechanism. However, there are some difficulties using RMG. So some current challenges RMG is facing is that as the species or the systems gets larger, there will be combinatorial explosion in number of possible reactions and possible isomers. And currently, it will be difficult to generate a fully detailed model for larger than 20 carbons systems by RMG, even with some memory saving techniques like filter reactions or pruning. So one of the possible solutions is that trying to maintain the species at certain size during modeling can effectively limit the possible numbers of species and reduce the memory requirement. For example, if we look at the right-hand side plot here, the x-axis is the carbon number in the feedstock. So if we look at the blue line here, it's the full detailed modeling method. So we can see as the carbon number increase, the total number of distinct molecules will increase a lot and make it soon to be intractable. However, if we somehow try to maintain the species size, let's say within 5 carbons or 8 carbons, then the red line and the orange line here shown here we can see the total number of distinct molecules will still be trackable. So instead of tracking every species, we could instead keep track of molecular fragments that will behave similarly. So now I'm going to introduce the auto-fragment modeling AFM. Since RMG tracks the concentration of every isomer, it assumes similar components to react similarly. So we can instead keep track of molecular fragments that will behave similarly. So the idea of fragments is trying to maintain within being smaller than the whole molecule, but larger than tiny functional group. So the idea is to breaking down large molecules to reduce the computation cost and develop reaction modeling between fragments. So for example, if we look at here, originally we have a large molecule. Then the first step is trying to identify each functional group. And then the second one is trying to search some potential feasible cutting position, which will avoid directly cutting at the functional group itself. And then after performing the cutting, then we will have a set of fragments, which will, as you can see here, attach some R's, which is called cutting label on the cutting position. And this is the workflow of AFM. Basically, it follows the same strategy as the normal RMG job. So the first step is to prepare the input file, which has fragments or molecules. And then it will use AFM and RMG to have to generate the fragment model. Once we have the fragment model, we can further use some simulators such as Cantera or Camkin to help us do some post-processing calculation. And the final step is trying to resume the molecular information by doing reattachment so that we can get the information that we really care about. For example, such as molecular weight distribution. So I'll first start with talking about how to generate fragments. So here we can see, suppose we have a starting material which is really large, then by searching for some potential cutting position, then we will have pseudo atom which is called cutting label, either R or L, attached on the each cutting position here. And we also define some specific patterns to avoid cutting at certain position. For example, the aromatic CC bond. So here are two types of patterns. The first one is the aromatic patterns shown here, and the second one is the aliphatic patterns shown here. And it will start from the most complicated patterns matching to the less complicated pattern matching. So here is the order to perform cut. And it used the subgraph isomorphism for checking substructures. And it will also use some constraints to maintain the fragment size within user specified range, which I'll talk about later. So currently there are two methods to generate fragments for the input file. The first method is to use the IPython script, which is called cut molecule into fragments, shown here. So you can just input the molecule smiles, and it can help you to get the output of a list of fragment smiles, so that once you get this, you can specify fragments and the corresponding molar fraction in the input file, such as here, either by smiles or by adjacency list. And the second method is to specify a large molecule in the input file so that it will automatically perform the cutting for you. And here is like the thing you have to notice is that you have to specify the cut to be true, and you can also specify the size threshold to make each fragment to be at least having like 5 here is at least having 5 carbon on each single fragment. So it will automatically redefine initial molar fraction and termination conversion. So the generated list of fragments will be printed out. So for example, showing here. And after specifying the species, then the next thing is to specify reaction conditions in the input file. So one thing we have to be noticed is that when you're specifying the pressure for fragments jobs, you have to multiply by a factor of initial pieces of fragment from the molecule. For example, if you're trying to simulate 20 bars for molecule jobs, then you have, and for example, you cut the molecule into 2 fragments, then you have to specify a factor of 2 for the pressure in the fragment input file, which is trying to ensure the same amount of initial amount in the system. So after we prepare the input fragments, then how can we estimate the thermochemical properties for fragments? Since a fragment itself is pseudo component, which has no clear definition of absolute values, but we can instead estimate the change of properties before and after the reaction. So we create representative molecule to obtain fragments thermal properties. So here's an example. For fragments in AFM, it will replace R with a somehow complicated structure and then estimate the thermal property of this whole molecule and assign the thermal property to this fragment. How can we estimate the rate constants? So here it follows the same idea about normal RMG jobs. We use the fragment to match the reaction templates and then map to the corresponding node in the hierarchical tree in RMG. So RMG will use either experiment or ab initio calculation data to estimate the kinetics parameters for fragment reactions. So once we have the fragment model, what should we do? As I mentioned before in the workflow slide, we can have some post-processing of fragment model, such as the reactor simulation, so that we can get a list of fragment concentration. And then we can do the recombination between the fragments to recover the molecular information. So here is the rest part of the workflow. So probably at this moment, after we have the fragment model, then we should ask one question: what information do we want from the model? So apparently we want to obtain the molecular information from the simulation. For example, the reactant conversion, the carbon number distribution, or the molecular weight distribution. And after reactor simulation, we only have a list of fragment concentration. So how to recover the molecules from the fragments? So one thing we have to do now is called a fragment recombination to recover the molecular information from the fragments. The first step is to categorize all the fragments into some groups. For example, the molecules or fragments contain only R, only L, or fragments which has R and L in it. And since the total number of R fragments equals to the total number of L fragments, so the practical steps in real algorithms is to grind the concentrations into several smaller unit pieces and then randomly shuffle them and pair each unit pieces. So here is an animation. So suppose for now we have already finished the pairing between the R labels fragments and with the L label fragments. And the rest of them are the fragments with both R and L cutting label on that. Then we can just randomly select some pairs to put them in. So that finally we can get the information of molecules. And here is the useful post-processing scripts, which is called the general fragment simulation reattachment. And once you use the script post-processing scripts, you can have the output to show the conversion profile or the molecular weight distribution or the carbon number distribution. And here are some application examples. So let's start with the simplest case, which is the octane one. And here I try to cut at the middle point to have the R fragments and L fragments shown here. So from the conversion comparison plot, we can see the fragment method. The fragment model is pretty close, has the pretty close result compared with the molecular octane model. By comparing the molecular weight distribution or the carbon distribution, we can see cutting will definitely lose certain connectivity information. The fragment method shows the potential of modeling alkane and similar product distribution between detailed and fragment model, as we can see here. And another more complicated example is you try to model phenylbutadiene PDD. So different color code here shows different cutting strategy. And here we try to compare the conversion and some important species concentration. So here, try to exclude the influence of recombination, we just compared the toluene concentration and the ethylbenzene concentration. So from here, we can see the random recombination might get us to have some large molecular weight species. And another thing should be noticed is that the cutting position really matters. So, so for here, we can see the yellow one has a really different behavior compared with all the other colors, also showing in the conversion plot here. So we know some really bad cutting strategy might lead to miss important pathway, and bad cut can lead to really different model behavior. For example, the yellow cutting strategy here. So if we try to use this fragment method to a more complicated system, such as here the 3-component surrogates. And here is the cutting position that I choose for the input. So for here, as we can see, by comparing the conversion or the total radical concentration, or even the total double bond concentration and the total CH3 functional group concentration, we can see the fragment model has really close behavior and results compared with the molecular method. And what if we reattach fragments and compare directly with the experimental results? So as we can see here, the red dots are the experimental result and the blue dots are the fragments result. So 3 time points shown on each plot, which is the time equals to 0, 3 hours, and 6 hours. As the color gets darker, which means the time passes. So for here, we can see the fragment method can successfully predict the aromatic chain species and the aliphatic chain species. However, there are some limitations on fragment method. Once the cutting is performed, some reaction might not appear in the model. So the end connectivity information will not be fully recovered. So we have to be really careful at the cutting position we choose. And some features are under development to optimize the method of cutting as well as the reattachment. Another thing we have to be noticed is that the size of each fragment will affect the speed of model generation and the chemistry. So for the problem of big fragments is that it probably may take too many computational resources and then slow down the simulation speed. For the problem of small fragments, which probably will get the small fragments concentration might affect the real chemistry, and also small fragments already itself has some really limited reaction to react, for example, showing here. So an ideal cold fragment renormalization could probably be helpful. After reacting for a certain time, we might have some poor size fragments, either too large or too small. Then the idea is to recombine them back to molecules and then recut them back to good size fragments. So during model generation, it might take too much time on reacting sites mapping or creating the isomers. So we don't want the process to be delayed. So probably perform cutting if large molecules are created can help us avoid this kind of issue. During model generation, if species size exceed the threshold, then we will perform the cutting in the edge. And if all species are moved to core, all the related reactions would be included into core as well. And for now, only a few reaction families will have this kind of issue potentially, which is the radical recombination and the radical addition to multiple bond reaction family. And we can also set the threshold of species size to cut. So for now, let's say probably the current threshold is once the species has more than 20 carbons, then it will cut. And once we perform the cutting, the reaction will be changed to be irreversible, which is shown here. But like, how about the reverse direction of the reaction? So we don't need to worry about that because the reverse reaction can be generated afterwards in the fragment form. So for example, shown here. Then let's discuss about the small fragments. So we can also set some thresholds for turning on the fragment renormalization, especially for small fragments case. For example, the total small fragment concentration, if it exceeds, let's say 25%, then we will do the recombine step with the timed interval this long. And one thing we have to know about one of the threshold is the number of core species, because we don't want to have the fragment renormalization to be turned on at the very early stage, since we don't really want to mess up the chemistry here. So if the small fragment concentration exceeds some threshold, then we will reattach the fragments and recut them to redistribute all the species concentration at some time point. And the simulation will continue with the new set of concentration of core species. So here is an example of using octane cut at the midpoint. So at T1, before renormalization, we can see we have a lot of the really tiny fragments, and we have some molecules already. So at T1 as well, after we do the renormalization, then we can see in the orange block, we can see that once we have combined CR with some CL into the species, which is already in the molecular form in the core species, then the species will not be cut once it's formed. So here you can see. And then we can see in the blue blocks that after doing the fragment renormalization, the number of really tiny, small fragments can be effectively reduced. So here's the conclusion that the detailed models can be generated a priori, and it's useful when collecting experimental data would be somehow slow or difficult. And AFM is now fully automatic. And this framework shows some potential to model many complex systems, for example, the alkanes, alkyl aromatic species, or even surrogate system. And this framework shows good model generation speed without sacrificing important chemistry. And the fragment renormalization is still under development. And if you have any questions, feel free to get the RMG website and the documentation, or look at the GitHub repo which is shown here. The link is provided here, or directly email me, and my email is showing here. So thank you. That's basically the brief introduction about AFM. And now I'm going to show mostly what people would do if you're having the fragments model. So
Can you zoom in just a little bit on your screen? Just the text is a little small.
Oh, sure.
Thank you.
So open the general frag simulation reattachment Python notebook. And first, we'll basically run all the cells in perfect. Just wait. It doesn't take very long. And I'll briefly go through what the cells are doing. So first we'll import the necessary packages. Looks like it's okay. And then the first part is to specify the condition and simulate the reactor. So if you put all the files in the my RMG files folder, then it would load the octane models, and then you can see if you can successfully load, then the number of the species in the model is about 265 species and 11,000 reactions. And then you can specify the temperature and the initial species and what's the corresponding molar fractions for each fragment. And here, one thing to remember is to modify the pressure for the fragment models. And because here we cut the octane into two different fragments, so now I have to multiply by 2 for the pressure. And also specify the reacting time. Here we choose 1 second. And then you will run the Cantera ideal gas constant TP reactor. And after simulated, all the data will be stored in the OData here. And then you can extract it to So the first list will be time. And then the second one will be the temperature and the pressure. And then you can calculate the total moles for the whole system at the initial time point and the final time point. So the initial time point, the initial volume for stacking in Cantera is 1 cubic meter. And for the final time volume, you can extract it from the model.volume mole. And the second part is to calculate the reactant conversion. So I have to reload everything so that I can plot. Yeah. So basically, you will probably get this plot about the conversion. And the third part is to plot the molecular weight distribution. And to do this, we have to do the fragments recombination. So the first step is to calculate the total R in our system and the total L in our system to make sure if both are consistent, are at the same amount. Because at every cutting point, we are generating the exact same amount of the R and L cutting label. And then we'll try to, and then here we specify more slightly advanced reattachment functions, which is mainly dealing with if you have more complicated fragment model, which you has some fragment has like more than 3 cutting labels, like 2R1L or like 2R2L or even more, then you will try to reattach them. Like, for example, if you have 2R1L, then you will try to
extract another species which has one R to attach to this, and so that you can reduce one L from the original to L1R. So basically, by doing this, we can finally get a different list. The first list is that if you have the fragment which has like 2R or 2L, it's basically just one of the R and L, and then you can modify the number of the moles of the fragment in the list. And for fragment with both R and L, we'll keep it like at the very last point. So first, we'll deal with the. Going to first. This block is basically dealing with 4 continental species. Yeah. And at this point, we'll check again if we still have the balance amount for the R and L. And then we'll define the grind size, which is basically how much pairs you are expecting, like it would randomly shuffle and divide and then match. So basically, if the grind size, like you can set it into like 0.5, that means for the total R, you have 253.33 moles for R fragments, and then you will decide to grind it in like, for here it's to be 1 mole, 1 mole, 1 mole for each. So that means you can expect to have 253 numbers for each list, and then they'll randomly shuffle and then pair up. So that after pairing up, you'll get like the list, the pairs which is stored in the matrix random, and then finally you will try to randomly pick the species which has both R and L fragments, like to be inserted in the already having pairs. So then finally we can calculate the fragment weight distribution for each single pair. And you were supposed to have you were supposed to be able to plot the molecular weight distribution, which is shown here, like this plot. And you can also modify the range. If you look at the bar chart here at the axis, you can specify the range up, because up a little bit here. And then you can also plot the carbon number distribution. Also save it to the results folder, so that you can also extract it and plot it in somewhere else. So here we read the CSV file, and we plot it here this moment, so you can see the x-axis has the carbon number from 0 to 17 or 18-ish, and the molar fraction for each carbon number species. Does anyone has any issue for running the Jupyter?